Let's imagine that you're swimming in fresh water. So for fresh water, rather than salt water, we know the density is 1,000 kilograms per cubic meter. Now, up at the top, what is the pressure at the surface of the water? Well, we still have all of the atmosphere above there, so we know the pressure at the surface of the water is 1 atmosphere. So we'll take P1 to be 1 atmosphere. In other words, 1.013 times 10 to the 5th pascals. Let's figure out how far down would you need to go until the pressure down here is 2 atmospheres. So let's imagine that P2 is 2 atmospheres. In other words, you've increased the pressure on you by 1 atmosphere as you have gone down. How far do you have to go down? What is H so that the pressure due to the water has increased by 1 atmosphere? Well, 2 atmospheres would be 2 times this, or 2.026 times 10 to the 5th pascals. So how far down do you have to go until P2 is 2.026 times 10 to the 5th pascals? Well, let's see. We know that P2 equals P1 plus rho GH. So P2 is 2.026 times 10 to the 5th pascals. And that equals P1, which is 1.013 times 10 to the 5th pascals, plus rho GH. Now for fresh water, we know rho is 1.00 times 10 to the 3 kilograms per cubic meter, times G, 9.80 meters per second squared, times H, and H is what we're looking for. Okay, so we'll subtract this from both sides. 2.026 minus 1.013 is just 1.013 again. We'll divide by the 1,000 by the 9.8, so H is 1.013 times 10 to the 5th pascals divided by 1.00 times 10 to the 3 kilograms per cubic meter times 9.80 meters per second squared. Divide that all out and you'll find that H is 10.3 meters. There we go. For every 10.3 meters, approximately 31 feet, for every 31 feet down that you go, the pressure is going to increase on you by 1 atmosphere. Now, I think this is very, very interesting because I have gone down to the bottom of a pool before that is not even 10 meters deep, and the pressure is definitely, you can definitely feel it much higher. My sinuses feel like they're going to explode, or maybe not explode, contract. And so 10.3 meters, that's pretty deep, and that is definitely something that you would feel. But what's interesting is that's what we're actually experiencing all the time right now, and we don't even notice it. We have that pressure of 1 atmosphere pushing on us, and we don't notice the pressure, we don't feel it, because all of that pressure is equilibrated. We also have that pressure inside of us pushing out. Now, there's some time that you might notice a little bit of change in that pressure if you've ever gone up in an airplane, or if you've been driving somewhere and changed your altitude, but especially with an airplane because it's very fast, if you've noticed that pain in your ears, that's because the air pressure from the outside has decreased. You have less air pressure pushing on your ears, but you still have initially that same pressure pushing out on your eardrums from the inside, and that can be very, very painful. To equilibrate that, you have to, swallow or chew gum or something like that to allow the pressure inside your eardrums to equilibrate with the pressure outside, so you don't experience that difference in pressure. It doesn't hurt anymore. Okay, so that is definitely something that you can feel, but we do not notice that 1 atmosphere of pressure that's acting on us all the time, as long as you're in atmosphere. Okay, let's take a look at one way that we might actually measure pressures. Let's imagine that we have an open container of some fluid here, okay? So it's just an open dish, so to speak, with some water in it. Now let's imagine we take a tube with a closed end and we put it down in the fluid and we remove all of the air inside the tube. So we pump out all of the air so that inside is a vacuum. In other words, what's the pressure? Well, if it's a vacuum, the pressure would be 0. Now, what's that going to do to the level of the fluid? Well, that's going to pull the fluid up the tube. So the fluid level in the tube will go up. It will rise up to some level inside. Does it go all the way to the top? Well, let's just imagine it goes up to some level for the moment. We'll just say some height h. Now, let's think about this for a second. Let's imagine you are out here at the surface of the fluid. What's the pressure out here? Well, there's still atmospheric pressure, so out here the pressure will be 1 atmosphere. Now, let's imagine you go down just a little bit so you can get underneath that lip of the tube. The pressure will increase a tiny bit due to whatever this distance is here, rho g d. Let's say if this is d, rho g d. Then you come over here and go back up. The pressure will decrease by that amount, rho g d. You'll be back to 1 atmosphere. So at the same height in the tube, the pressure is going to be 1 atmosphere. Now, where is that pressure coming from? It's coming from this fluid that is above that height. Now, the pressure up here at the top, we know, because this is a vacuum, the pressure up here must be 0. So we'll think of that as P1. P2 is down here, so we have P2 equals P1 plus rho GH. P1 is 0, P2 is 1 atmosphere, so we have 1.013 times 10 to the 5th pascals equals P1 is 0, rho GH. So let's say if this is water, say pure water, not ocean water, fresh water, then what would the height be that this level would be? Well, we've already done that. Remember, that would give us h is 10.3 meters. So we'd have to have a very, very long tube, but if we could do that and evacuate all the air out of there, the water would go up to a height of 10.3 meters. And then, by measuring any fluctuations in that height of the water, we'd be able to determine what the atmospheric pressure was. This would be a way of measuring atmospheric pressure, by measuring what that height is, and then putting in h, take rho GH, and figure out what is the pressure, and that would tell us what the pressure was out here, if atmospheric pressure varied from the 1.013 times 10 to the 5th. If this was a little bit less, say 10.2, we'd have a day with a somewhat low pressure. If we had 10.4, we'd have a day with a higher pressure. So, by measuring what that height is, we can use that to measure what atmospheric pressure is. This is what we call a barometer. Now, there's a couple problems physically with making a barometer like this. First of all, it's got to be over 10.3 meters tall. That's a very, very tall barometer. You wouldn't be able to keep that on your desk, for example. Also, if you had it outside in winter, well, the water's going to freeze. Anytime you had a day below 32 degrees, the whole thing would freeze. Well, a couple ways of getting around that is to use a fluid that does not freeze at 32 degrees, but can go much lower. And also something that's much denser than water. We wouldn't have to have such a tall barometer. Well, a great possibility would be, well, this has got its own problems, but what was often used was mercury. Now, mercury has a density of 13,600. In other words, it has a specific gravity of 13.6. It's 13.6 times denser than water is, which means we would be able to make a barometer that was 1/13.6 as tall. Also, mercury doesn't freeze at 32 degrees, it freezes much lower, so we'd be able to use it actually during the winter time. Now, if we were to actually put the density of water in here, the density of mercury in here, we would find that H was 0.760 meters. We could have one of these that's less than a meter tall, and that would be much more reasonable height for something like that. You would be able to have something like that on your desk. Where 1 millimeter of mercury is actually used sometimes as a unit of pressure itself, and it's called 1 torr, and it's equal to 133 pascals. Okay, great. What other ways can pressures be measured? Let's imagine we have this very peculiar looking sort of thing where we've got some fluid over here, or some gas, maybe a gas or something like that, at some pressure over here. But let's imagine for the moment that it's the same pressure as our atmospheric pressure outside. Now here we've got a tube with an open end, so we've got atmospheric pressure here, if that's the if we assume the pressure in here is the atmospheric pressure. They're both pushing on some fluid that's in this U-shaped tube. Now, if the same pressure inside is the pressure outside, then the level of the tube here will be the same as the level of the fluid. The level of the fluid here will be the same as the level of the fluid over here. Now, let's imagine that we have a pressure in here that's actually greater than 1 atmosphere. Well, that's going to push this fluid level down and push this fluid level up, so that this fluid will be pushed down while this one will be pushed up like that. Now, we know that the pressure here, if we start with the pressure here of P2, we come down, over, and back up. We know that pressure has to be the same as the pressure of the fluid over here at the same height. Let's call this P2. And P1, the pressure up at the top of the fluid, which is 1 atmosphere. We know again that P2 must be P1 plus rho g h. In other words, the pressure here above atmospheric pressure will be rho gh, where h is this height that this fluid level is above that fluid level. So we could use this device to figure out what the pressure in here is above atmospheric pressure. We could use it to measure that pressure P2. Well, this is actually how blood pressure cuffs work. You can imagine putting your arm in here, and this thing is around your arm, and the nurse or doctor, whoever is measuring your blood pressure, pumps it up and increases the pressure of the air in here, and then there's a device measuring what that pressure is, and they can then determine the pressure of the air in the cuff by the difference in heights in these fluids. Now, I know this is how they used to be done. Blood pressure cuffs can measure pressures differently now, but I remember when I was young in particular, there'd be this big tube on the wall, and as the nurse pumped up the blood pressure cuff, you could actually see the tube of mercury, the column of mercury going up the tube. But this particular type of pressure measuring device is called, if you've never heard one of these, a sphygmomanometer. Sphygmomanometer, the blood pressure measuring device. Okay, very, very good. Now, how can these pressures of fluids be used? Is there something that we can do with them? Absolutely there is. Something very, very important. Let's take a look. A very important idea regarding pressure is Pascal's principle. And it states, any change in the pressure applied to a completely enclosed fluid is transmitted to all parts of the fluid and the enclosing walls. So, how does this work? Let's think about this. Let's imagine that we've got a container, kind of an odd looking container here, but a container with some fluid in it, and over here there's a side tube with a little piston over here. Now let's imagine that we push on this piston. We apply some force on it here. Well, what's going to happen? It's going to push the fluid in, and this fluid level will rise. But what if this entire fluid were sealed in? So let's imagine that this whole container was closed off but filled with this fluid. So the fluid is filling this whole container. Now, let's imagine we apply this force. We push on this piston. What's going to happen? Well, there's nowhere for the fluid to go. This force here, in other words, this increase in pressure, which would be the force per area, if this tube had a cross-sectional area A, if we increase this pressure by pushing on it here, that pressure is then exerted everywhere in the container. So that pressure is at every single point within the walls of the container, but also everywhere within the fluid. The pressure in the fluid everywhere increases by this same amount P. So whatever force we apply here, whatever pressure we apply, the force per area, that pressure increases at every point within the fluid, including at every point acting on the walls. Now, how can this be applied? Well, let's take a look. Let's imagine we have kind of this odd U-shaped tube here where we have one narrow opening here and one wider opening here. Let's imagine that this narrow opening has some cross-sectional area A1, while this larger opening has some larger cross-sectional area. We'll call it A2. Now let's imagine there's a piston over here, a small piston of area A1 that moves up and down in this tube, and a larger piston of area A2 that can move up and down in this tube. And let's imagine that this whole tube, both sides, is then filled with some fluid. Okay? Now, let's imagine that we apply a force on this piston. We push down over here with some force F1. Well, that's going to apply a pressure, P1, that's equal to F1 over A1. Well, according to Pascal's principle, that pressure is going to be distributed through the entire fluid, all the way over onto this piston as well. So there's going to be a pressure increase pushing on this piston of P1. Well, that's going to create a force upward from this piston. We'll call that F2. Now we know that the force over this area is equal to the pressure, so we know that P1 must equal F2 over A2. That's the pressure exerted by the force F2 distributed over the area A2. But we know that P1 is F1 over A1. Well, multiplying by A2, we know that F2 must equal A2 over A1 times F1. Now, notice we arranged this so that A2 was much larger than A1. Well, that means A2 over A1 is a very large number, which means F2 is much larger than F1. This is a way of increasing applied forces to get a much larger force. So we might have a small tube over here with some pump pushing on this tube over here, pushing on the fluid over here, which will actually increase the amount of force being exerted over here. Well, this is the area of hydraulics. And if you've ever taken a car or seen a car taken to a workstation in a gas station or a service station or something like that, and they drive the car up onto the two tracks that hold the tires, and then this giant metal cylinder can come up and just lift that entire car right up off the ground. Well, that's this tube here with hydraulic fluid underneath pushing it up. But you do not need to apply a force on the fluid that's equal to the force being exerted by the piston pushing the car up. You can exert a much smaller force with a hydraulic pump, applying a smaller force as long as the area of the tube over here is much smaller than this tube. You can exert a much, much smaller force. So hydraulics is a way that you can actually increase this applied force increase the amount of force that's coming out of this tube and be able to do some pretty incredible things with it. Okay, very, very good. Now, what else can we do with fluids?